Thank you for joining my webinar today. I'm going to go over the Functional Safety Lifecycle as defined by IEC 61511 and how to tackle the tasks of the design and implementation phase using exSILentia. This is part 2 of this webinar, so if you're interested in the analysis phase, I recommend checking out part 1. I'll start by introducing myself. My name is Kate Hildenbrandt. I'm a product manager at exida for our exSILentia software. That means that I help the team to define requirements for new functionality within the software, as well as optimizing existing features based off of feedback. I also help with customer support and training. And I've provided my email address at the bottom of the slide so that if you have any questions for me, whether it be on our software or on exida at large, you can use my email address to reach out and ask me that question. I can answer it myself, or I can put you in contact with the best source for the answer. So please don't hesitate to use that email address and reach out with your questions. A little overview on exida. We do have 3 main groups within exida. We have an engineering team that provides consulting services for functional safety, alarm rationalization, and cybersecurity. We also have a development team that creates software to help with those same tasks. We do develop the software in-house. And we have a certification team that does FMEDA analysis on devices used across multiple industries for safety instrumented systems. We also certify personnel with our CFSE and CACE programs. So hopefully with these 3 main groups, we can help you with your needs as they pertain to functional safety, alarm rationalization, and cybersecurity. To an overview of the safety lifecycle. IEC 61511, and this is what the lifecycle looks like within the standard. It's basically taking you from hazard and risk assessment, or PHA, of a process or system, looking for any high-risk hazard scenarios that could occur, and taking a look at what safeguards are present to protect against them or bring the process to the safe state. You want to document requirements for that safety instrumented system. You want to design it according to that design criteria, and also communicate requirements for implementation before installation, before testing, and commissioning. Then obviously, as the safety instrument system is running, you want to operate, maintain it. You want to collect data on its performance, do any modifications if needed, and ultimately decommission the safety instrumented system. And this diagram always looks like a bit of a checklist to do all of the things needed to maintain a safety instrumented system until decommissioning. But from our viewpoint, we really do look at it as a life cycle, because we're really focusing on the data flow from task to task within the software. What I mean by that is when you're documenting your PHA, you're really taking a look at the whole process and trying to see if there are any high-risk scenarios. And for those scenarios, you're going to document the cause of the scenarios and the consequence, as well as any safeguards that could protect against that hazard. And ultimately, for the ones that are most high risk, you're going to go forward into a layer of protection analysis. And since you've already documented the causes with an exSILentia, those will come over into the LOPA as initiating events. And your safeguards will come over into the LOPA as potential IPLs. You'll determine if they're independent, and you'll take a look at the frequency of that hazard scenario given the IPLs that you have. Once you meet that target frequency, you're going to be able to say which of those IPLs are safety instrumented functions. Those are automatically going to show up in your SIL selection tool, where you can determine the target SIL or the target risk reduction factor. With an exSILentia, this can be done based off of your LOPA results. You could also do it with risk matrix or risk graph. Finally, this becomes one of the requirements for your Safety Requirement Specification, where you address all of the different requirements that you want to pass on to the design team. We basically have a field for everything that's called out within the standard to be included in the SRS. And together, all of these analysis tools allow you to have the information that you need when you go into SIL verification. In SIL verification task, you're modeling your SIFs. So you have your requirements from the SRS, and you're trying to reach your target SIL and your target risk reduction factor. You're going to define the architecture of your SIF. You're going to choose the equipment that you use. And you can use our database to choose equipment and very easily have all of the data you need, from failure rates to proof test coverage, useful life, and so on. And ultimately, you're going to choose your proof test strategy. So how often are you testing your SIF during the O&M phase? Once you've entered all the different parameters that SIL considers, you're going to have a result, and hopefully that result meets your target SIL and your target risk reduction factor. If you have to change anything in order to meet that, you might use our lifecycle cost estimator, which will help you consider cost and how to optimize cost, as well as reaching your safety integrity requirements. So you might have a decision between adding more redundancy or testing more often, and that's going to help you make that choice. Once your conceptual design is complete for your safety instrumented system, you can communicate the design requirements for implementation using our design SRS. And now that you've pretty much set in stone the structure of your SIF, the equipment that you're using, your testing strategy, you're able to communicate more detailed requirements than you were in the safety requirement specification. Perhaps you've had to meet or exceed those requirements. And now that you've chosen your equipment, you're able to also communicate better requirements for those. So the design SRS is meant as a handoff for the implementation team. For operation and maintenance, we also have tools for proof test generation, alarm rationalization, and recording of events during the life of your safety instrumented system. We're going to talk about the proof test generator today, where you're able to take a proof test provided by the manufacturer for each piece of equipment that you've included in your safety instrumented system. You can define if you want to write proof tests for an entire SIF, for the different groups of the SIF, or for specific devices, depending on how you usually do your proof testing. And we'll provide for you the testing steps that the manufacturer suggests. These are important because they're used as the basis for the proof test coverage within SIL. And that means based off of the steps in the procedure, we're able to determine how many dangerous undetected failures are revealed during the test. And so you want to make sure that you're doing those steps. It's possible that you're doing even more effective proof testing. And so by reviewing those steps, you might be able to say, hey, we're doing something extra here, and perhaps our proof test coverage should be adjusted to account for that. The proof test generator provides these steps and allows you to apply them to an editor, which allows you to put in steps that might be site-specific or application-specific, and still make sure that you've accounted for the steps that the manufacturer suggests. And so we'll walk through how that works in a little bit. With alarm rationalization, our SIL alarm tool allows you to rationalize and prioritize your alarms to make sure that the operator has time to effectively respond to each alarm and bring the process back to the safe state. And our SILstat tool will help you to collect data during the life of your safety instrumented system as it's online. It's going to help you to keep up with the proof testing that you've specified, record any device failures, any process demands on the system, and see the performance of your safety instrumented system and if it's meeting the assumptions you've made in analysis and design. And so we really do see this as a full life cycle, especially from a data flow perspective. When it comes to the analysis phase, in part one, I did go through the PHA, the LOPA, and the SRS. And what we're going to do now is walk through SIL verification, design SRS, configuration of your safety logic, and proof test definition. And we're going to talk a little bit about each task, and then I'm going to show you some slides Giving a high-level overview of how we would tackle these tasks within exSILentia. Then I'll open the software itself and walk you through them. Talk a little bit more about phase 2. SIL verification, what you're doing is you're modeling your SIF to determine the conceptual design. And so here you are going to specify the SIF architecture, the equipment that you're using, and your proof testing strategy. Then in the design SRS, you're going to document all requirements needed to hand off to the implementation team. Another output of your SIL verification is the ability to automatically configure your safety logic for a Delta V system. Within exSILentia, we're able to, in Silver, define the inputs and outputs and the relationship between them. And so we're leveraging much of the work that you've already done to help you get started on that configuration of the safety logic for Delta V. So we have a tool that creates an FTX file that you can then bring into Delta V, and it will configure your safety logic for you. The results of this should obviously be reviewed, and you might have to massage a few things, but the idea is we're providing that traceability and consistency and allowing you to use work you already did to get started on the next task. For proof test specification, we can use the proof test generator, which is going to allow you to define those functional tests for your SIF devices by providing you the manufacturer-specific steps that they would suggest for a proof test, and then allowing you to add steps to make it easy for your techs to do those tests on site. So let's look at how we would do this in the tool. First of all, just to highlight the fact that within the tool, we have a database. We call it the SCRH, which is Safety Equipment Reliability Handbook, that provides failure data for thousands and thousands of devices. And this is an example of a data sheet within the SCRH. You don't have to refer to this at all when you're modeling your SIFs. You can just choose your equipment and it's going to apply the right failure rates. But I do think it's interesting to take a look at the type of data we're providing. So this is just a generic ball valve. And you'll see that there are a few sets of failure rates here. It considers if you are in a clean service application or not, and that just means are you in an application that the device was designed for. It considers if you're opening on trip or closing on trip, if tight shutoff is required, if you're doing partial valve stroke testing or not. And you can see, dependent on those selections that you might be making in the tool, you would get the appropriate set of failure rates. We also have things shown here like safe failure fraction and useful life. The useful life should be used as a basis for your mission time. You can see response time up here, which is calculated by the tool along with the other results. And you can see the data source. Many of the data sheets you'll see are FMEDA analysis done by exDA, done by other sources, or comprehensive analysis. You'll be able to tell if the devices you're choosing are SIL certified because they'll be in bold, but we also provide many devices that are not SIL certified. And so again, within the tool, you'll just be able to choose your equipment by clicking through, but this is the type of data that is applied. It also comes with those proof tests, so we do have the proof tests embedded along with this failure data. When we start in Silver, and I will open up the software in a bit, but I would like to walk through some of this here in the slide. The first thing we're going to do is define our proof test at the top. Our SIF at the top level. So we're going to give the SIF a name and a description. We're going to give the SIF a tag. You can indicate who is modeling the SIF from your team members within your exSILentia project. You can give it a date. Whenever you first modeled this SIF is going to be the default date, but perhaps if you've updated it, you would be able to come in and choose the analysis date. And you can link any design references. Obviously, this is rather broad by attaching the entire standard, but in reality, you might have some drawings, some equipment drawings, or even a PNID that you want to link here from the library. You'll be able to indicate which units the SIF is in with the units. And all of this is referenced. So when you're defining these top things, these are just going to help to define what your SIF is doing. The next few selections will impact your calculation. So you're able to choose your architectural constraint basis. We have two choices, IEC 61511 and IEC 61508. You're able to decide if you want to consider SIL capability. And if you're choosing a certified device, this is very easy. If you're not, you would have to document a proven and use justification. You can do that within exSILentia. If you choose not to, you can uncheck this button. If you already have a work process for doing your proven and use justifications and you'd rather just add it as a reference and link it here as a documented proven in use, you can easily just not have the tool calculate that result here. Next, you can specify your as-designed mission time, your startup time, your demand mode. If you're doing batch operation, we can account for that. You can decide if you would like your I/O channels on separate modules within the logic solver for the SIF that you're modeling. And if you'd like to consider mean time to fill spurious in your. Once you've defined your SIF, it's going to automatically give you 3 SIF parts that you can continue to model out. So it will provide a sensor part, logic solver part, and final element part, where you can then create the groups and legs that make up your SIF. And this provides quite a bit of flexibility within exSILentia. For the sake of this example, we are modeling a pressure measurement on a batch reactor. And I think we're going to get into the details of this batch reactor in a bit. But basically, you can give your sensor a name, a description, your sensor group, and you would be able to then indicate how many sensors are in your group. So here I have 3 sensors voted 2 out of 3. They're identical. And you can see here the beta factor, the mean repair time, and a group mission time can be specified in the group options. So over here you can see I have 3 sensors, but I really only have to specify what equipment I'm using once, so that because they're identical. So that's a bit of a time saver. We do have your proof testing strategy, which you can input the interval for proof testing. You can indicate if it's performed online. If so, are you staggering the testing between the different transmitters? Do you have alternative protection if a hazard occurs while you're doing the proof test? What is the duration of your proof test? And you have the ability to override the proof test coverage provided by our database if you'd like, by just clicking this override data button. If you'd like to see the data we're providing, you can do that. Again, that's based off of your selection of a device from our SCRH, and it's based off of the manufacturer's suggested proof test step. When you're defining your leg, you can give it a name and a description. Here you see I have PT 501A. I can go down here to give the other 2 a name, but again, I only have to specify the equipment once because they're identical. So I can choose a measurement type, and in this case, it's pressure, a trip setting, a transmitter fault direction, and I can also specify if my PLC can detect certain things that are happening with my sensor. So if my signal is out of range, does my PLC know? Can it do external comparison? And what happens if it is? Does my plant trip right away, or does it have a bit of a trip delay? Then you can specify the devices. Here I've chosen generic process connection and a generic pressure transmitter. And so that gives you an idea of all of the different parameters that we would consider for a sensor. Next, you can choose your logic solver. Here again, I've chosen a generic logic solver from our database, but our database has a number of options. And here you can do a proven in use justification directly for the logic solver. You can indicate if you need a logic solver specific mission time. So if your entire SIF is going to be completely replaced or refurbished every 20 years, perhaps that's based off of your logic solver. But we saw in this last one that we set a group mission time for this sensor of 10 years, and that would be based off of a shorter useful life for the sensor. So here we have a group mission time for the sensor, and we assume the logic solver will be changed out at that 20-year mark, because we haven't given it its own mission time. We have a mean repair time for the logic solver, the proof test information, so the interval and all of that, override equipment data, things like that. You can see the different modules are being assigned as you model the SIF, and so you're able to walk through and see that as well. You can specify final elements. Again, we're just creating one final element group. We're giving it a name and a description. We can set the vote. This would be 2 valves on a reactor drain line that are voted 1 out of 2. And here you can see that they're also identical. You can see the mean repair time. There is no group mission time here. A proof test strategy is specified with an interval. We have overridden the equipment data to put in our own proof test coverage. And we have basically chosen equipment for the final elements. So we have a generic solenoid and a generic actuator valve assembly. So here you can see all of the parameters that we're considering specifically for the final element. Once your SIF is modeled, you can see the results. And if we take a little bit of time to look here, you're able to see the risk reduction factor, the PFD average, and the mean time to fill spurious for each part of the SIF. So the sensor, the logic solver, and the final element, and then the overall result for the entire SIF. Your achieved SIL and RRF are shown here, right next to their requirement. That requirement can be entered directly if you're starting with silver, but if you've gone through the whole life cycle, it will already be there from your SIL selection and your SRS information. You can see your achieved SIL according to your PFD average, according to your architectural constraints, and if you're considering SIL capability within the tool, you'll be able to see that here as well. I have documented my proven and use justification for these generic equipment elsewhere, and so you're seeing not applicable. But we know our achieved SIL is the minimum value out of these 3, and so we're seeing that I have achieved SIL 1. You can see the calculated response time. We do have contribution charts, so you can see the contribution from each part of the SIF to the PFD average and to the mean time to fill spurious. And so if I wasn't reaching my target SIL, I might focus on my final elements because that has the largest contribution to the PFD average. Once my SIF is complete, I can go on to document requirements in the design SRS. And what you're seeing here is that same SIF with the same name, same description, and its requirements within the design SRS. The SRS modules are like templates that help you by providing a field for each of the requirements called out by the standard or important to our users at large. And so you see a number of fields here that you can fill out for the SIF. Right away, you can see that my sensor group name is in here because it's pulling a lot of the SIF modeling that I've already done in silver into the design SRS so that each section is really based off of part of the SIF that we're addressing in the requirements. And so you can see all of the different requirements here. You see common cause sources. You'll see the trip delays, voting degradation scheme. All of that can be defined here. Obviously, in a screenshot, I can't show you the entire SIF, but we will open up the tool and take a look at that. On this side, you can see general SIF requirements. So for some of these fields, you would be able to define them once for your safety instrumented system and apply them to each SIF all at once. And so that's a little bit of a time saver, especially if these are consistent across the board for each of your SIFs. If they're not, you can always apply it and then change it here in the SIF specific panel if that's a little more time friendly. But yeah, you would be able to do that in the generic SIF requirements. And so with the design SRS, what you're doing is you're going to generate a nice consistent report in Microsoft Word that shows these requirements in the same structure every time for the SIFs that you've modeled in Silver. And again, this is meant as a handoff to the implementation team so that they are aware of all the requirements needed to install this in your system. Another output, as we mentioned from Silver, is the ability to create an FTX file that can be used to transfer into your Delta V system to automatically configure your safety logic. And so this is an example of that where you're seeing basically your sensor, your voter block, your valve output here. And so here you're seeing all the parameters that are considered in this automatic configuration of your safety logic. For the sensors, we're looking at the number of input channels you're voting. Is it high or low trip? Does the logic solver detect out of range signals? Are there any trip delays? And you can see, tags, range, trip point, all of that. For the final element, we're really looking at number of output channels, your tags, and the action needed. And some of the design SRS information is accounted for as well. So maintenance overrides, trip delay time, auxiliary inputs and outputs are all considered when generating this FTX file. And so this is, again, a good way to jumpstart this task. It still needs thorough review. It still might need some massaging, but you're taking advantage of the work you've already done in Silver to get started on this part. And for now, we have this for Delta V. So if you have Delta V, you would be able to take advantage of that. Finally, we want to highlight the proof test generator because even though we're not in the O&M phase yet, you're not necessarily doing the proof test, you do want to define your proof test procedures. And you want to do that so that it lines up with the proof test coverage and the proof test strategy that you have already outlined in your SIL verification. And so these screenshots are just highlighting that we have these steps embedded in the database for each device. Even generic devices have steps that we have input into the database based off of, in this case, pressure transmitters across the industry. So we've looked at the different manufacturers' suggestions for these tests, and we have defined the test, and then the proof test coverage that is used is based off of the dangerous undetected failures that could be revealed by doing this specific test. And so whether you're using generic or manufacturer specific, you can account for these steps within the proof test editor. And in the proof test editor, you can account for a few more things. You can add any site-specific steps, any detail to the steps that are required for your application, and you can also add pass-fail criteria. You can see here, you can basically define if a person is out at site performing the test, you know exactly what value they should get, what tolerance you're willing to accept, obviously the unit of measure. In some cases, you might just want a check mark to say, yes, I've done this step. And this is all going to be included in a report that it generates. If you would like to use our SILstat software, you can also import your proof test into it and perform the proof test directly in the software. So there's a couple different ways to use this data, but what we really want to do is make it easy to create the proof test and also make sure we're accounting for those steps that are used as a basis for the calculation you just did in Silver. Now that we've gone through that, let's talk about a practical example. And then I'll open up exSILentia itself and we'll walk through the same tasks that we took a look at here. In this case, we're looking at a batch reactor, and we have a few things going on here. With this batch reactor, and again, this is just an example process that we're using as a basis, but you're basically having two materials, A and B, fed into the reactor. And the reactor has a few pressure transmitters. So you have PT 500, which at a certain pressure is going to open this vent valve to an incinerator. You have PT 501, which if it reaches a certain pressure is going to sound an alarm. And it's also going to control an interlock 3. So interlock 3 does a few things. It's going to dump the contents of the reactor into a large quench tank. It's also going to control the input of feed B into the reactor, since that's the one causing the high pressure in this sample project. And it also controls the feed coming into basically a jacket. So we have chilled water coming into a jacket and also processed hot water coming in to control the specific temperature needed for this reaction. And so if this pressure gets too high, it's also controlling which water comes in, chilled water into the jacket on the reactor. And so there's a few things from a safety perspective that we would want to highlight. If we look at that high pressure scenario, you might have a high risk hazard happen if your valve here does not open to vent to the incinerator. And so if that is your cause for the hazard scenario, let's look at a few of the different safeguards that are here. If you have that, if we say that normal operating pressure is 10 psig, we have a high pressure alarm at 15 psig. So that's your first high pressure alarm when this pressure transmitter detects high pressure. So it's going to sound an alarm, and we expect the operator to respond to that alarm to bring the process back to the safe state. We have another alarm at 20 psig, and that is when our SIF reacts. So in this case, PT501 hits 20 psig, which is going to open our final element here to dump the contents of the reactor into a quench tank, and that happens at 20 psig. There is another safeguard here in the design, which is to say that if our SIF fails, there is a rupture disk, PSC 500, right here, that's going to lift at 60 psig and obviously relieve the pressure within the reactor. So this is our high pressure scenario, and this is the same one that we walked through in part 1 of the webinar. We walked through the PHA, we walked through the LOPA, SIL selection for this SIF, and the SRS, where we're defining requirements to model this SIF. And so it's really simple SIF where you basically have one pressure transmitter that lifts at 20 psig and opens a valve to the quench tank. So what we want to do is take a look at the next few tasks for this scenario. So we're going to start with SIL verification, and we're going to model that SIF together. So let me open exSILentia. I'll open up a sample project, but we're going to start with a brand new SIF. So hopefully you can see me presenting exSILentia here. And this is the dashboard that hopefully you got some idea of what this does within part 1 of the webinar. One thing I want to highlight for the design phase and SIL verification is the SCRH database. So again, this is our Safety Equipment Reliability Handbook. And if I click on that, it will open up a viewer. And so as I mentioned before, this is just a nice way to view the data. You'll be able to come in here and search. You'll be able to find the different devices that you might want to use, and you would be able to look at the data sheets that are provided with those devices. So this is the same one that we looked at within the slide, and you'll notice that the screenshot I had in the slide doesn't have all of the data that's associated with this device, because we also have a section for severe service. And that really means, are you using this valve in an application that it was not specifically designed for? And so in some cases, that would cause the failure rates to change. But here you can see, as we showed before, all of the different sets of failure rates, whether it's clean, service, or severe, whether it's open or close on trip, height shut off as required, and if you're performing a partial valve stroke test. You can see the useful life here, the safe failure fraction, the response time. You can see the data source. And so you'll notice that I searched here on generic, and this is simply the number of generic devices that we have within the SCRH. We have quite a bit of options here for people who perhaps haven't chosen the equipment that they want to use specifically and would just like to use reasonable data, maybe a little on the conservative side, but reasonable data for these types of devices. Obviously, if I take the filter off, you would be able to see all of the devices within the SCRH. The ones that are bolded are SIL certified devices, and so you would be able to see their SIL capability on the data sheet. The ones that are not bolded are not SIL certified, so you'll be able to do a proven in use justification within the tool, or you could document it elsewhere and just indicate that you've done it. Perhaps even save that justification within the library references and link it to the SIF. Sure. So when we're in Silver, we're able to choose the equipment without having to look at the data sheet. It's just a nice to have to be able to view that data. The SCRH is updated quarterly within exSILentia, so we're trying to always add more devices into the SCRH. Next thing I'm going to do is hit the Silver button up here, and you can see that that opens up my Silver tool. And I've already modeled a SIF here within Silver, and you can see its results. You can see the SIF diagram, and you can see all of the fields that I use to input important information in for the SIF. But instead of walking you through that one, I'm going to create a new SIF so we can walk through the SIF modeling together. So to do that, I'll hit the new SIF button, and I'll select the SIF itself. If I want to add a requirement, my required SIL and risk reduction factor, I can open up this view, which allows me to put in my requirement. In many cases, if you've already done some of the analysis work within exSILentia, you would be able to, already have this at your fingertips. You've already done your LOPO or your SIL selection, but I'm just going to enter it directly. So again, we'll say that the required risk reduction factor is 22 and the required SIL is SIL 1. So when I go back to my SIF definition, you can see those requirements here. That's going to happen automatically if I've done those other tasks. If not, pretty easy to enter in. One other thing I want to highlight is the SIF diagram starts out looking pretty simple. It is going to build itself out as I model my SIF. So here we have a high pressure protection SIF for my batch reactor. And I could give it a description here. I can say that at 20 PSIG, P501 causes to open, dumping contents into the quench tank. And I can also give it a tag here. So I'll call this SIF 501. I can set an analyst. The analysis date is the date. It's going to default to the date that I created the SIF, but obviously you can open a calendar and you can change that date if needed. Attach any references I have stored in my library here. I can indicate the unit. And again, all of this is reference. It's really just, there's even a comments field if you have any more detail about the SIF. It's really meant to help you to identify your SIF. Obviously, if you have done any of the analysis work, you're already going to have a good idea of what the SIF is responding to, and you'd be able to see that at a glance. So if I open up my other SIF, you can see a lot of the information is already filled out in that same view. You'll be able to see my basis for my LOPA. You'll be able to see some of the SRS fields and all of the silver fields right here. Within the library, you'd be able to see all the places that SIF is used within the project file and get a good idea of the hazard scenarios that it is responding to. So once I click on the SIF, I can see the sensor part, the logic solver part, and the final element part. And I'm going to move forward and fill out these next few parameters, which are going to affect my calculation ultimately. So for architectural constraints, I am going to choose the IEC 61511 tables. I can consider SIL capability or not. I'll leave that checked for now so you can see what happens with that, with the results. I have my mission time here, so I'm saying that after 20 years, I have to fully replace or refurbish all parts of the SIF. And so this mission time affects every piece of equipment in the SIF. When we do our PFD average calculation, the average is taken over the mission time. Next, we have our startup time. How much time does it take to start up the plant after a spurious trip? Our demand mode, I'm going to say low demand here. You can indicate if you have batch operation, and it will ask you a few additional questions about time between batches, and it's able to account for that. We have the ability to indicate if you want your I/O channels on separate modules in your logic solver for this SIF. And I will say yes. And then I can decide if I want to consider mean time to fill spurious in my results. And I will say yes. And so once all of that is defined, we can move on to defining the sensor. And so I'll select the sensor part here, and I'll add a group. And here I'll say that this is my pressure measurement on batch reactor. I could give it a description. I will leave that out for now because I don't want to make this too much of a typing exercise. I can go down to my group options and set a vote. In this case, it is 1 out of 1 pressure transmitters, so I can just adjust the legs to match the vote. And what that will do, if we go back to the navigation tree, is you'll see my group and you'll see my leg. And in this case, we just have 1 pressure transmitter, so you're just seeing 1 leg. I can enter my mean repair time. So this is the time it takes after my pressure transmitter fails to replace or refurbish it, reinstall it, and bring the process live again. And so that's my mean repair time. And we're defaulting to 24 hours. In this case, we can also add a group mission time. So I'll say that I am going to have to replace this pressure transmitter at the 10-year mark because its useful life is 10 years. So I got to make sure that I'm changing it out before the useful life ends. Then I have my proof testing. So here I can indicate a proof test interval. I'll leave that at 1 year. I can also say if it's performed online or not. So if it is, I want to indicate if it has alternate protection. If there's redundancy, it'll say, are you staggering the testing between the pressure transmitters? It'll ask for the duration. I can override the proof test coverage if I want to. I don't want to, and I haven't chosen my equipment yet anyhow. So you won't be able to see coverage there. So what I'll do is skip down to the leg, and I will give it a name. So this is PT501, and I will say that this trips the SIF at PSIG. And I'll choose a measurement type. So you can see all of the different measurement types that are available within exSILentia. Other, level, temperature, flow, proximity, fire, gas, and pressure. So I'll choose pressure. And here I can indicate if it's a high or low trip. So we're tripping at high pressure, and I'll leave it there. Next, I can indicate if there's an internal fault in my transmitter. Do I want it to drive the signal under range or over range? And so those are my 2 options, and I'll select under range. Next, I can choose a process connection. So you see my devices are available here. For a sensor, I can choose a process connection, a sensor, and input interfaces. I could click this large button to get to the database. I could click this UD button to create a user-defined device. So if you don't want to use our database or you don't see the equipment that you're specifying in our database, you can always define a device model within exSILentia. It will be stored in the library, and you can use it over and over again throughout your project, just like you would from our database. You can also link device models that you've used before within the project. So if you really don't want to go in and search through the database over and over again, it saves the ones that you've used recently, and it'll make them readily available for you. In this case, I'll go into the SCRH, and here you basically see the same viewer that we showed a minute ago. You can view the data sheet in here as well. So this is a nice way to choose your data. Again, the bolded items are SIL certified and the non-bolded items aren't. And to choose generic in these scenarios, and since this is a process connection, what I want to type in is cleans. So I'll choose this generic impulse line, and it's just assuming that no plugging would occur within my application with this process connection. And so I've selected it. I can look at the data, and I can just click Add Device. Next, I'll choose my sensor, and here I can input generic, and I can choose my pressure transmitter and hit Add Device. Now that I've chosen an analog device, you'll see there are more options for PLC detection configuration. So here I can choose if my logic solver can detect out of range signals with my sensors, if I have a transmitter fault filter, if we're tripping on transmitter fault, and if there's any external comparison. These obviously external comparison, if you have redundancy, would help you to see any frozen signals. But basically, this is going to help to determine the classification of your failure rates. So if you're failing high or low, is that a spurious trip? Is it a dangerous undetected failure? These selections help to determine that within the tool. And if you hit the group details, you'll be able to see exactly that. So here I can see what I have specified. I can see the name of the equipment, and I can see the different failure rates in black, but I can also see how they're classified in yellow. And so that is based off of the selections I just made. So I've modeled my sensor part. I'm going to go into model my logic solver. And what I can do here is I can either choose a logic solver that I've already specified in my project, which makes sense if a lot of them are using the same logic solver. It will know that it's the same exact logic solver. Or I can specify one from the database. So let's again search through the database for a generic SIL 3 certified PLC. I can expand this, and you'll see that my pressure transmitter is already accounted for within the module. So we do have a logic solver builder within Silver that will show you the different inputs and outputs as you're modeling your stuff. You can also specify a logic solver mission time. We'll assume it needs to be changed out at that 20-year mark. You can specify your MRT and your proof test strategy here. Finally, we will define our final elements. So you can see how the SIF diagram is building as I go. I'll add a final element group. I'll say that this is the valve on outlet of reactor. And then I will set my group options. Again, this is just one valve. Here I can set my proof test strategy, and I'll just use the defaults. I'll say that I'm proof testing once a year, and basically that I'm doing it offline. I'm not going to say that we're doing a leak test or doing the test at operating conditions because I'm going to just assume that I'm using the proof test that is provided by the manufacturer. Then I can give my final element leg a name, and this is XV500. Then I would be able to specify the equipment. Within Silver, you're able to specify things that aren't remote actuated valves. So if I hit Other, this is going to show me a list of motor starters, relays, all sorts of things that could be a final element but is not a remote actuated valve. So I would be able to specify an output interface and an Other. Everything else here is geared towards those remote actuated valves. So you could have a full remote actuated valve assembly. We have a few of those in our database. You could specify a separate solenoid and then specify a pneumatic element if needed, an actuator valve assembly, or specify the actuator and valve separately. And so you'll see as I start to select my equipment, some of these options are going to turn off because they don't make sense with what I'm choosing. So the first thing I'm going to do is go straight for the solenoid. And I'm again going to choose generic. And I will choose a pilot operated solenoid from this list. And you'll see as soon as I do that, these options go away. So they know I've chosen a remote actuated valve. And so the other option is grayed out. I've specified a solenoid, so it can't be part of a full remote actuated valve assembly. And so you'll see some of the other options go away as I go through. The next thing I'm going to do is choose an actuator valve assembly. And it's already got my filter on it, so I can come in here and choose this air-operated ball valve. Once I do that, it's obviously not going to let me specify another actuator or valve. Now that I've specified my equipment, I can select these leg options. So we're going to say that the valve is open on trip. And we're going to say that it's not in severe service. So it is appropriate for this application. We're not putting any additional stress on it. And so you can see here my final results for my SIF. You can see my SIF structure. You can see my sensor going into the logic solver, controlling the valve. And it's very simple SIF, just one sensor into the logic solver controlling one valve. Sadly, you'll notice that I have not achieved my target SIL or my target risk reduction factor. And there's a few things to point out concerning that. So number one is that the achieved SIL is going to be the minimum of my SIL according to PFD average, my SIL according to architectural constraints, and my SIL according to systematic capability. And obviously, I have a few zeros here with systematic capability because I chose generic equipment. And so my achieved SIL is ultimately 0. You'll also notice the results per SIF part. So you can see my achieved RRF, my achieved PFD average, and mean time to fill spurious for my sensor, my logic solver, and my final element, my overall SIF. So in this case, let's assume I've done proven and use justification, that I have used the equipment that I am basically representing as generic here for years and years, and I have good justification documented outside of exSILentia. I could come in here to consider capability, and assuming I have that well documented and possibly linked here, I can uncheck this box, and I can see that my achieved SIL is 1, and my achieved RRF is 13.9. So I still haven't achieved my RRF. The other thing you could do is just go into the database and choose SIL certified equipment. For the sake of time, I'm not going to do that. One other option is within exSILentia, you can do a proven and use justification. So if I say go into the pressure transmitter and I want to do the proven and use justification, I would be able to do that within exSILentia. So I could create a new one, and it would allow me to basically look at a number of requirements for devices that aren't certified and justify why I think that they're appropriate for the application and document my rationale here, attach any reference documents, and say what I believe the systematic capability. That is something you can do within exSILentia if you don't already have a work process for that. And it's a nice consistent way to do it. You'll see I still haven't achieved my RRF, and my biggest contributor to my PFD average is the final element. So let's say that I realize that I might need, in this case, to proof test more often. Let's see, it's already 1 year, so that might not be something I'm dying to do. But let's say I proof test every 6 months instead. Didn't really help me there. So what else could I do? Look at the proof test coverage. My proof test coverage is 67%. Perhaps I can go into the proof test steps and say, I am doing a leak test and I am doing my proof test at operating conditions. So I can come in here and say that perhaps the proof test coverage, which again is the number of dangerous undetected failures that are revealed during the proof test, I can enter 90%. In that case, I have achieved my risk reduction factor. Now, that all seems very casual within exSILentia. I'm casually saying I'm going to do this proof test every 6 months and casually saying I'm sure that my procedure has a coverage of 90%. None of those things are casual, but you can see how the different parameters work to account for all of the things that you're doing on site for your safety instrument and system, and basically give you an accurate achieved SIL and achieved RRF. One other way to take a look at the impact of the parameters within exSILentia is to look at the PFD charts. So if I open up these PFD charts, you'll see that we have a graph of the probability of failure on demand and the trend of that probability of failure over the life of your SIF or over the mission time. And so you can see it increase, but for different tests, you'll see it then decrease. And over time, it still trends up. And then the dotted line here is the PFD average. So that's the average over the mission time. If you change the mission time, you would see that average change as well. So if I go into my SIF and I say, we're actually going to change this out after 15 years, that's going to have an impact on that average. That's why it's so important that at the end of the mission time, all parts of the SIF are fully replaced or refurbished. So you can see then that's taking the average over the 15 years. So this is the PFD chart for the entire SIF, but I can also see the PFD chart for the sensor group, the final element group, and the logic solver. The sensor group looks quite a bit different. That's because at 10 years, we are fully replacing that sensor. And so if you'll remember, the group mission time was at 10 years. And so you can see the impact that has on the sensor. We'll have the logic solver showing the effective proof testing, and the same with the final element. One other thing we could do for the final element, let's say there's no way we're testing every 6 months. We'll put it back to a year. But we will also change this out at 10 years. And because that final element contributes so much to the PFD average, you might see a larger effect for that than you did for the sensor. So in the overall SIF PFD chart, you're seeing that final element mission time show up. And so as you play with the parameters within Silver to get an idea of what they're doing to the calculation, looking at the PFD chart is a really good way to check out the effect of those parameters. Each of these pixels is being calculated by our SIL calculation engine. We have a time-based Markov model SIL calculation engine within exSILentia. And so you'll be able to see the effect then of these different parameters. And you'll see that we have achieved our target RRF doing that. Another thing that's a nice usability feature within Silver is the SIF Overview feature, where it's going to allow you to basically change out or bulk edit some of the parameters that you set. So if you have hundreds of SIFs in here and you do want to change your mission time, as I just did, you'll be able to select the SIFs. You'll be able to go to the mission time and change it and apply it to all SIFs. And so let's say here I want to change this guy to 15 years as well. Obviously with 2 SIFs, it's not as exciting, but you'll be able to do that with this parameter update. So this is going to help you to basically do big changes. Say you're revisiting your design and you realize that I didn't set the proof testing intervals. I left them at 1 year, and now I have to be able to set them, but I know I'm testing everything at 4 years, and so you can use that to come in and change that. So the next do is move on to the design SRS to show you, and I'll use my top SIF, but just to show you the different requirements that we're considering within the design SRS. And this is really built based off of what we've done in Silver. So you can already see the SIF name and description. You have to define your SIFs within Silver for them to show up in the design SRS, but once you do, they show up automatically. And you'll be able to see here my pressure transmitter from my first SIF. Got the same tag. So obviously a similar example, but you can see that group here. And for that group, you can see all of the requirements that pertain to the sensor. The overall sensor requirements are up here. You'll be able to see the specific leg requirements here. You can add any auxiliary legs parameters, any shutdown hierarchy. And then you'll see you can do the same for the logic solver and for the final element. For the first SIF, we have 2 valves here, so you'll be able to see the final element leg. Anything that is universal to all of the SIFs can be set here in the general SIF requirements. And I don't think I have it set up here, but you can set up a shutdown hierarchy. And this is going to produce a nice consistent report that mimics the UI in that all of the requirements are in the same order, in the same spot, and easy to see when this is handed off to the implementation team. As we mentioned, many of these parameters are also considered in the sys logic. So when we come in here, we can produce an FTX file that is going to take the work that we did within Silver and within the design SRS to automatically configure the safety logic. Unfortunately, I am not able to show that right now as I do not have access to a Delta V system to be able to show you that. But if you have any questions on that, please reach out and we'll be happy to schedule time to show you exactly how that works. Finally, the proof test generator is going to take a look at all of your equipment selections and provide the associated steps from the manufacturer. So if I go to my proof test, I can create a proof test, and it's going to automatically show for my generic pressure transmitter, my generic logic solver, and my valve, solenoid and valve, the steps that come along with that. Obviously, with generic, it's a little less exciting than when it comes from the manufacturer, but you get the idea. Over here, you see my empty proof test editor, and I can take each step and apply it, or I can apply them all at once and say, hey, I just built a full proof test for my SIF based off of the manufacturer's input. Then I'd be able to come in here and add anything else that's needed. So that includes any site-specific information, any application-specific detail that maybe needs to be added to these steps, or even you would be able to add pass-fail criteria. So let's say that I want to add the ability to say, I know that during this step, we want to see a number equal to 3.6 milliamps. And that I would say that it passes with a tolerance of 0.1. And so that's something that would be included in a report that is generated, but also if you have or have interest in our SILCDAT application, this can be imported in and you can use that to determine if the test failed or passed if you're doing the test directly within SILCDAT. This, again, it's going to generate a nice report if you're not doing that, or even be able to be imported into another tool that you're using to keep track of those proof tests. And so that is how we're taking care of the design and implementation phase of the lifecycle within exSILentia. There's obviously a lot of good functionality here. I didn't even really get to touch on the cost module, or even all of the capabilities of Silver, as we just modeled a very simple SIF. But hopefully that gives you an idea of what the tool is capable of and how transition from task to task can be made easier using the full Safety Lifecycle Suite. So as I mentioned at the top of the presentation, if you have any questions for me, please feel free to reach out. I'd be more than happy to answer anything on exSILentia or anything else that Exita does. And if I can't answer it, I will make sure to put you in contact with somebody who can. And thanks again for joining today. Take care.